Hello dear friends, welcome to a lecture on complex analysis. In this lecture we shall study continuity of a function of complex variable. This definition I have written which is similar to the definition of continuity of a real valued functions. Only the difference is here z may approach z naught in different ways, and in real variables if you write x approaches a, then it will approach towards x will approach towards a from left and from right along a horizontal line or real line along this real line, and this point is a. Then x will approach from right or from left. But if you consider z approaching z naught in complex plane, then z will lie in the neighborhood of z naught, and that will approach z naught in any manner in this disk. So, that is the difference, and here a function f is continuous at a point z naught if all of the following conditions, all three of the following conditions are satisfied. Now, what are these conditions? The first is limit of f of z at z tends to z naught must exist. So, this we have to check the continuity at this point z naught, and the function's limit at z tends to z naught must exist. The second condition is the function's value at z naught must also exist. So, these two are different, limit of function f of z at z tends to z naught and f of z naught, these are different, and the third condition is these two must be equal, limit z tends to z naught f of z must be equal to f of z naught. Then we shall say the function f is continuous at point z naught. Actually, this is the only condition for continuity, because if this holds, then when we say these two are equal, these first must exist, and that means this exists and these are equal, then the function becomes continuous at point z is equal to z naught. And we will write the same definition in using the definition of limit, that is a function f of z is continuous at point z naught, at a point z naught if for every, we are using the definition of limit, if for every positive number epsilon there exists a positive number delta such that this approaches to f of z naught, such that absolute value of f of z minus f of z naught is less than epsilon whenever z approaches z naught, and this z minus z naught is less than delta. So, what is the difference here made is this is not deleted neighborhood of z naught, it is this neighborhood may contain the point z naught, and because actually it must contain, because we want the value of the function at z naught, this must exist, and therefore, this is the alternative definition of continuity, and we will use this definition for proving results. Now, we will prove a result, and you see, if f of z and g of z are continuous at z naught, at z is equal to z naught, then so does their addition, subtraction, multiplication and quotient. Then f of z plus g of z, f of z minus g of z, f of z into g of z, and f of z divided by g of z, provided g of z is z naught is not equal to 0. This denominator at value of g z at z naught is not 0 are also continuous, and this result follows according to the earlier result that we have proved. So, what we have proved is the limit of f of z plus g of z is equal to limit of f of z plus limit of g of z, and therefore, if f of z is continuous and g of z is continuous, their sum is continuous, their difference is continuous, their product and their quotient is also continuous. So, now we will prove a result as theorem. Composition of two continuous functions is continuous. The composition of continuous functions is itself continuous. This is the result we shall prove, and first we shall see what is composition of two functions, continuous functions we have to consider. Let first function we shall consider w is equal to f of z be a function defined in the neighborhood we will consider of z naught, z minus z naught less than delta of point z naught. This is the function defined in this neighborhood, and further we will consider another function which we will denote by capital W and g of z be a function defined whose domain of definition is the image of this delta neighborhood, is the image of z minus z naught less than delta under f. So, in this way we have considered two functions, first is f and then is g. The image of the domain of g is image of f, and thus then w is equal to see g of f of z. See, we have to consider here g of w, here w is f of z and here capital W is g of w. Then w is equal to g of f of z, g of w and w is f of z, is a function whose domain is or is defined in the neighborhood of z minus z naught less than delta, and we will draw a figure for this. First we shall say consider this function w or the function f, and see we will have like this z plane, and we have to consider the delta neighborhood of z naught, and I shall consider this as delta neighborhood of z naught. Anywhere we can consider, this is z naught and this is delta, and z will be a point inside this disk, and then we will have its image, this under f. The image under f we may show like this, not necessary in the first quadrant or second quadrant, it may be anywhere in the plane, and here this is f of z naught, this point is f of z naught, and this is the radius of this neighborhood, and we shall denote it by gamma. Instead of delta, we will denote it by gamma. And a point f of z will lie inside this neighborhood. So, this is gamma, and a point will be f of z. So, distance between f of z and f of z naught is less than gamma whenever distance between z and z naught is less than delta, and the mapping is from this neighborhood to this neighborhood by the function f. And again we have to consider function g. So, this is the uv w plane, and this is capital W plane, and its neighborhood can be considered like this. And this is the center point, and it is G mapping. So, it maps this point G f of z naught, and its image will be G of f of z naught. And a general point will be G of f of z, and this is within epsilon neighborhood that we are considering. These are the images we have. First is the neighborhood of z naught, and then that is under f, it is mapped here, and then the domain of G is image of this neighborhood here, and G maps this neighborhood to this neighborhood, and that means G of f of z will be mapped to G of f of z here. F of z will be mapped to this point, and f of z naught will be mapped to this point. Now, what we have to show that if f and g are continuous, then g naught f, that is this w is continuous, that is we have to show. Let f is continuous at point z naught, and g is continuous, or let f be continuous at point z naught, and let g be continuous at point f of z naught. We will use this condition first. G is continuous at point f of z naught. Since G is continuous at f of z naught, for every, the definition of continuity we have written in this form, epsilon delta form, for every positive number epsilon there exists positive number delta, and instead of delta we will consider it as gamma, number gamma, such that these are Greek letters to denote small positive quantity epsilon, delta, gamma, and instead of delta, because delta is used here, we use gamma. We are using continuity of G, such that, now how to write it, this is continuous, means the difference is less than, difference of these two is less than epsilon whenever the difference of these two is less than gamma, such that absolute value of G of f of z minus G of f of z naught, yes, is less than epsilon whenever absolute value of this f of z and f of z naught is less than gamma. We assume this as statement 1. And now we use continuity of, we have used continuity of G, now we use continuity of f. Since f is continuous, f is continuous at see, it is continuous at z naught. For we have for every positive number gamma, every positive number gamma, there exists a positive number delta. We are using now gamma and delta. There exists a positive number delta such that absolute difference of f of z and f of z naught is less than gamma whenever the absolute difference of z and z naught is less than delta. Now, we suppose this statement as second. We now combine 1 and 2. Now, see what statement 1 says, this is absolute difference of g of f of z minus g of f of z naught is less than epsilon whenever this difference is less than gamma, and this is continued here. Whenever this difference is less than gamma, then we this happens whenever mod z minus z naught is less than delta. So, combining these, we will get this difference is less than epsilon whenever this difference is less than delta. So, combining statements 1 and 2. What we will get is, we get mod of this g of f of z minus g of f of z naught is less than epsilon whenever this z minus z naught is less than delta. So, what this shows? This shows that g of f of z is continuous at this point z naught. So, this that means the composition of two functions is continuous, or in the form of limit that can be written as limit z tends to z naught of g of f of z is equal to g of f of z naught, and this proves the composite function. That is g of f of z is continuous at z naught, at point z naught. So, this is what we wanted to prove. The composition of continuous functions is itself continuous. So, this is the result that we have shown. Now, we shall prove the second result I have written as theorem 2. If a function f of z is continuous and non-zero at a point z naught, then f of z is not equal to 0 throughout some neighborhood of that point z naught. That is to be proved. So, function is continuous and non-zero at this point z naught. So, we shall first apply the definition of continuity. Since f of z is continuous at z naught, we have for every epsilon, every positive number epsilon, there exists a positive number delta such that this difference f of z minus f of z naught is less than epsilon whenever here the neighborhood of z naught is z minus z naught is less than delta. And now, what is given is this function is non-zero at z naught, given f of z naught is not equal to 0. So, therefore, we select epsilon as this is the non-zero, and therefore, we select epsilon as absolute value of this divided by 2. We choose we select epsilon is equal to mod of f of z divided by 2, because epsilon is every positive number at our choice, and therefore, we can take epsilon as mod f z. Mod f z is positive, and this is because this is non-zero, it is positive, and we have divided it by 2. And then if you write this value of epsilon here, we get then we have, so this is the earlier theorem we have proved. Then what will be this? Then mod of f of z minus mod of f of z minus f of z naught is less than epsilon is mod f z divided by 2, and whenever z minus mod z minus z naught is less than delta. Now, we shall suppose this as a second statement, and what we want to prove is f of z is not equal to 0 throughout some neighborhood of that point, and we will suppose f of z is 0 for some neighborhood. Then what will happen? If f of z is equal to 0 in some neighborhood, in some neighborhood of this point z naught, then from 2 we have what the second statement will imply as this is 0. See, mod of 0 minus f of z naught is less than mod f of z divided by 2, or see, we should consider here this point as z epsilon as f of z naught divided by 2, and then this is because this f of z naught is not equal to 0, and therefore, this will be f of z naught divided by 2, and this is f of z naught divided by 2. Epsilon is at our choice, and we should select epsilon as a value having this one. And what will if this is 0, then 0 minus f of z naught is less than this quantity, or that means f of z naught, absolute value of this is f of z naught, mod of f of z naught is less than half of mod of f of z naught, which is a contradiction. A value cannot be less than half of itself, positive value, which is a contradiction. And this contradiction proves that f of z must not be 0, or that is non-zero. This proves f of z is not equal to 0. F of z is not equal to 0 in some neighborhood. In some neighborhood of z naught, and thus this proves the result. See, one more result can be considered as if f of z, I shall only quote that statement, if f of z is continuous on a closed and bounded region. This is also a theorem. Closed and bounded region R, then there is a positive number m, such that absolute value of f of z is less than or equal to m. So, this follows from the definition of closed and bounded region that we have seen earlier. So, we know a region S of complex plane is said to be bounded if we have mod z is less than or equal to some particular number, that may be m or any other number, and then this S is said to be bounded, and function is continuous and that is on closed and bounded region R. Then we have that there exists a positive number m such that the absolute value of the function is less than or equal to m. So, these are some results regarding the definition of continuity and the composition of continuous functions. I hope you will understand this. Thank you for watching the lecture.